Hi everyone, I'm really excited to be here at Artucon this year. My name is Ahmethan and today we are going to talk about how VM-based obfuscation works on Android. Quick introduction about me. My name is Ahmethan and I am working on mobile application security and the reverse engineering stuff at the byte area. Today we are going to go over a few topics related to virtual machines. First, we will learn how a VM actually works. The second one is VM hardening techniques, like we will explain control flow flattening technique and dynamic opcode table technique and other techniques like that. The final part is the devirtualizing VM-based protection. We will research the Google's new security protection tool is the PayIP protection. So that's our agenda today. The first one is understanding virtual machine fundamentals. A virtual machine takes normal instruction and converts them into custom opcodes. Basically, VM structures work like a mini CPU because they have their own opcodes and their own execution loops and similar internal processes. So each opcode is processed by a small function we call the handler function inside the VM, while a dispatcher runs that loop that fetches opcode and decode them and execute them. So we are calling these loops to FDA loop, fetch, decode, execution loop. We will explain in the next page. This extra layer changes how to code loops and makes reverse engineering much more difficult. The VM hardening techniques I'm mentioning here will be shown later in the slide page. So this is the from instruction to VM bytecode page. Here we can see how a normal program to get converted into VM bytecode. In original code, we push the values 5 and 4 onto stack, perform a multiplication process. Then we take a result, then multiply by 3, and the final value is the 16 we get. So it's the normal original code process. So when this code is converted by the VM, it replaces those normal operations with its own opcodes. So the push and multiply instruction become VM specific opcodes, like the 0x5 is we push, so 28 and 25 bytecode is the pushing to stack the 5 value. So in the end, we get something like this VM bytecode, a simple example of how regular code turns into VM bytecode, because we have an original code and we are mapping to VM opcodes for this code. And the final, we have encrypted VM bytecode. So if we look at the little bit visually, the byte 2A in our bytecode represent the push operation, because we know the pushing 5 number to the stack. So 2A operands means virtual push. So this line pushing the 5 value to the stack. And the next line has same process again to 2A push operand and the pushing stack to 4 value. After that, the opcode is 3B is the multiply operation. So it multiplies the top 2 values on the stack. In this case, we have 5 and 4 value. We keep that result on the stack, then use 2A and 03 bytecode again. So we are pushing to 3 value to the stack, and we are making another multiplication process. So we have this result and multiply again. So we get the final result. So this is a simple example showing how a VM reads and executes its own bytecode step by step. So basically, we have 4 main components of the VM: VM entry, VM exit, VM dispatcher, and VM handlers. So VM entry point is entry point into the virtual machine. initialize the context state, jumps into the interpreter loop. Its section is our VM's entry point. The VM exit point, it is termination of the virtual machine, loop ends, context cleaned, and returns to control to native code. So basically, we have 2 points, and one of them the entry point in this VM. The second one is the exit point to termination to all context stuffs. So we have one entry and one exit point. The dispatcher is the most important thing of the virtual machine structure because the VM dispatchers are the main router of the VM because all opcodes and all operands are routed from the dispatcher. The dispatcher section reads the current opcode and transfer to control to the appropriate handler. So we often don't know what an opcode does until we trace to its handler. So we have VM entry point and this branching to VM dispatcher. So VM dispatcher fetching the current opcode and this opcode, which handler related to this opcode, this handler routed to this function's handler. So VM dispatcher point is the most important thing of this VM. This FDA point means fetch decode execution loop. The VDA loop is the most important part of the VM. The loop does 3 things actually. We have fetch operation, the next instructions fetching, the read opcode and operands. After that, we have decode process, what that instruction actually means. Finally, we have instruction and what the instruction actually means. So we need to execute these instructions and method. So it's the final part, execute part, the instruction by calling the proper handler. If there is no router and no dispatcher here, you can't resolve the which instruction does what. So dispatchers route us to the handler for each opcode. This is why we need to dispatching system and why dispatchers are most important thing of this VM. So the handler functions is the code block that implements the semantics of a single opcode like push operation and add operation and jump operation. So each handler represents the one opcode. Basically, we have one opcode and this dispatch loop the pointing to one of the handlers. So we know this handler related this opcode. This means one opcode could be means the push, making a push operation, and other one is making an add operation. So this handler function is the main business logic functions of this VM. So we have 2 important things of the VM structure. One of them the fetch decode execution loops, and the other one is VM handler loops. So the basically handlers typically implement semantics like push, pop, and arithmetic operations, memory operations, and other control operations. The function prologue is the setup phase because we have a different context to our computer. We have another VM context. So we need to save current frame pointer and save the return address and to create space on the stack for the local VM variables. After that, we have function prologue. It's basically the cleanup phase because we have a lot of VM context, VM stack, VM local variables, and other VM stuffs. We need to clean this on the exit phase. So the epilogue is the cleanup phase. It restores the save registers, restores the stack, restores the frame, and returns to the caller. These patterns are useful for markers when locating to handler boundaries and reconstructions control flow. There is 2 examples to prologue concept and epilogue concept. So we have the 2 common virtual machine types. The one of them is stack-based VMs. The The stack-based VMs operands are pushed and popped from a stack. It's traditional VMs using the stack-based VMs. The instructions are simple and compact than the register VM because for the basic process, we pushing to 5 value to the stack, and after that we are pushing to the 3 to the stack, and then we have some add operation, and these 2 values adding in the stack, we have 8 value. It's the traditional approach of this VM. We are calling to stack-based VM. After that, we have register-based VMs, use named slots like R1, R2, and R3. We have same process up here. After that, we have a different boxes here because we have R1 register, R2 register, and R3 register. The difference is we store all values and all operands into the stack of the stack-based VM. But for the register-based VM, we are making all operations into these registers like R1, R2, and R3. So we are pushing to 5 value into R1 register. After that, we have the push operations again to 3 value to the R2 register. Finally, we have add operation to R1 and R2. Then these operations store the result to R3 register. So finally, we have 8 value is in the R3 register. So that's the 2 common virtual machine types is here. Okay, we have a lot of information about the virtual machine context. The next step is how developers make the VMs harder to analyze. We will explain to some popular VM hardening techniques. The first one is duplicating VM handlers. Duplicating handlers means taking the same handler. We can call this slide to H function, H handler. So this making copies to like H1 and H2, H3. They all performs the same semantics. They all of them the same functions, but we have the handler table, VM handler 0, and after that we have H1 and H2 and the original H. So this basically is a duplication method of this VM because we need to a little bit complicated the handler table of the obfuscation step. So if we have to one original function and a lot of fake another duplicate function, maybe we will complicate handler table more easily than the other methods. So it's a simple but effective confusion trick of the obfuscation side. The control flow flattening is a super common trick. The control flow flattening is basically when clean simple code gets rearranged and into one big loop that jumps around to using state variable. It's a quick way to hide original flow and to make the code harder to flow. So we have normal program control flow grab, and after that we have some making control flow flattening operations. And after that, we have a lot of handlers and we have a big dispatcher loops to different the normal program. So that's the most common trick of the obfuscation. The word is the control flow flattening. The final part is the hash-based dispatching. The hash-based dispatching, instead of using small opcodes, values like 0x1, 0x2, and 0x3, the VM can use 33-bit hash values, often VNV opcodes. The opcodes looks like random numbers like 0x63CB and other characters like the other opcodes, which prevents the easy prediction and the brute forcing of the dispatch table. So we have an example, normal VM to 0x1, 0x2, and the hash-based dispatching VM have a lot of hash-based opcode values. So It has some disadvantages for the reverse engineering because these opcodes looks like a little bit longer than the traditional VM opcodes. So this makes static analysis harder. We cannot guess what's the next opcode, and it prevents the trivial patching, the must recompute the hash. So it's blocking to tampering applications a little bit harder. We will see it used in the real life on the next page because the Google PayIP VM has same protections of the PayIP. So we will see how to use them. Okay, the virtual machine hardening techniques is ended here. So let's switch the gears and look at a real example to PayIP. The PayIP is updated version of the safety net mechanism because in this year Google is ended of the support to PayIP protection and making a new protection system. This name is PayIP. The PayIP has similar mechanism to safety net as basic checks because the both of them has some integrity checks on the device like root check and tampering detections, the Frida detection, and other some integration tricks. The one most big difference is PayIP has VM-based infrastructure, a huge heavy obfuscated VM methods and encrypted bytecodes and hash-based dispatching VM. The PayIP has every handler processes a VM instruction in a fixed pipeline. The parse operands, execute logic, and hashing and verifying to VMV1 hash mechanism. So we have a lot of the integrity checks to bypass the PayIP protection. So it's execute VM method control flow graph. The execute VM method is the most important thing of the PayIP because it's the main method of the PayIP protection. So we will see how we can dump this method's binary in this next page. The technical analysis is the basic call chain is the invoke to get VM bytecode, execute VM, and return execute VM. But after that, we need to know some informations about the PayIP. So the bytecode files storing in assets folder. In this picture, we have some bytecodes like these files to pointing to lines. Bytecodes are executed by invoke method on Java side. The basic call tree is invoke method, the call to bytecodes, and this bytecodes the converting get VM bytecode method. And after that, this sending to execute VM, the main method, execute VM processed and executing this bytecodes here. And finally, the execute VM returning to or return value here. The encrypted bytecodes are first decrypted in the execute VM method. Execute VM method is the registering using the register VM GNI method. So we don't see it to static analysis because this method is registering by the register natives at the runtime. So if we have to JADEX and the other compilers, if we want to look where is the execute VM method running, we don't have any fingerprints here because this method is registering at the runtime and using by register natives call. Execute VM method is not existent SO library. We already talked about this because implementing with the register natives call, if we want to look closer, we will need to pull it from the runtime memory. Okay, we have enough information about the PayIP protection. Let's open the app in JADEX and take a closer look. So I have an example app for the closer researching. Let's open the search button and we search to VM Runner. We have the VM Runner class inside the com PayIP package. Let's open. And as you can see, we have the execute VM native methods is here, declaration is here. So its return type is object and this method's taking the two parameter. The first one is byte array VM code parameter. The second one is object array RGS parameter. So we know where is the declaration to the execute VM method, but we still don't know where is the execution point, where is the registration point. So we need to hook register natives with some Frida script and some Python tool, and to find real execute VM address and execute VM's binary. So let's come back to the slide. We will back here in a little bit. Okay, we have enough information about the PayIP, so we can make a Frida scripting and Python scripting. About the Frida step, we can use enumerate symbols call in the Frida, get the register native offset, and after that we can use interceptor call in Frida, hook DL open call to Android. If the PayIP core SO is loaded in the memory, hook register natives call and get execute VM's real offset. As you can see, we have some outputs is here, but let's try the example app in the terminal screen. So yeah, we have some Android emulator and some Frida scripts is here. I can publish these all scripts in the GitHub repo. So we need to execute source virtual environment being activate. We are in the virtual environment. So Python, where is the Python script? So yeah, dump PA and execute them. We have some large outputs is here. So basically, we have some large outputs. Let's search the execute VM. So yeah, we need to, first of all, we need to register native point, and we are found this. GNI environment offset is here. The J class parameter is here. After that, we using the register native offset to the find execute VM method. To execute VM method is registering by register natives, and at the 0x1598F8 offset. So we know about where is the execute VM's real call, and after that we dump to this execute VM binary in the our machine to analyze the binary with the R2. So we have finally we have execute VM dump file to the looks like 5,000 kilobytes and dump successfully. So yeah, we have the execute VM dump is here. Come back to the slide. We are finishing about the Frida step. Now we can switch to R2 step. So for now we have the execute VM binary methods, and we have how to works this execute VM methods and PayIP protection systems here. So we need to analyze to execute VM methods. This binary is calling to execute VM.dump. The PayIP has heavy VM obfuscated structure like dynamic opcode table, chains at runtime, bytecode verification with the FNV1 hash system, executing encrypted bytecodes. We already talked about this, the address obfuscation, and a lot of VM hardening techniques. So let's take a closer look. The PayIP protection have a lot of the protection tricks in the binary, and this one is the FNV1 hash to bytecode integrity check. This slide shows how the PayIP protects its bytecode using an FNV1 hash. Each instruction is hashed during execution and compared with the expected value. So if it doesn't match, the VM just crashes. That's how it prevents to tampering the modification, because we have a larger and longer opcodes is here. For the reverse engineers, this makes it tricky because everything looks random and flows get a little bit messy. As you can see, we have some fingerprints in the binary. We have fnv1 constant init process is here. After that, we have the fnv1 prime value init process is here at the 0x52 CAC offset. And that is the example fnv1 hash loop in the binary. So we know about some information to fnv1 hash. Here is the normal traditional VM. It reads one byte from the bytecode, checks it in a switch case block, and jumps to the matching handler like add and sub or multiplication process. So we have a simple operands is here like 0x01, 0x02, and blah 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 like simple bytecodes. After that, this dispatcher has a simple switch case statement is here because we have simple opcodes, case 0x01 to routes to add handler, 0x02 routing to sub handler. So it's the basic traditional VM example is here. And now on the right, this is hash-based dispatcher VM. Instead of the clean opcodes like 0x01, 0x02, it uses to 32-bit hash values like 0x63 and the other opcodes is here. And one of difference is we have to switch case block in the traditional VM. At the hash-based dispatcher VM, we have a lot of if-else statements is here. So this adds randomness and makes static analysis much harder. It's an example for the bytecode integrity check. For the traditional VM, we have switch case statement basically. For the hash-based dispatcher VM, we have a lot of if-else statements is here. So the second part is opcode analysis. In this binary, we have a lot of opcodes is here. When we take a closer look, we often see move and move key pattern used when building opcodes. Like these lines, we have the move instruction, and after that we have the move key instructions. It's a lower part, it's a higher part of the opcodes. After that, we have a small CMP lines is here, and after the CMP instruction, we have the branch call to the handler functions of these opcodes is here. So that's a basic opcode and dispatcher relation example in the PayIP binary. If we check the methods that are called right after this pattern, we usually end up at the handlers. But it wouldn't be correct to call every piece of the code using move and move key parent opcode because we cannot say to all move and move key pattern to the point to the opcodes. It's a wrong information because we have same pattern is here and it's not an opcode. So we need to carefully analyze to which is the opcode and which is the different using is here. So, and this pattern is exist because on ARM64 binaries, you can't load a full 32-bit value with a single instruction. And if you want to load 32-bit value, you need to move and move key patterns use like this because we have at the lower part and the higher part, and we will merge this and we have the hash value opcodes is here. So to summarize, PayIP builds its opcodes using the move and move key pattern and then branches to the handler methods like these sections. Here we can see it in more detail. There is an example opcode area. The move and move key instructions are used to combine the low and high parts into a single opcode value. We have a simple opcode is here because we have move pattern and move key pattern. After that, we have using the CMP call, and the points to the after that we have the handler address. When we follow that branch, we see a simple VM call handler that calls two different methods. As you can see, we have to load arguments from the stack, argument 1, argument 2, call to native function at the BL instruction, check return value, set next opcode, and return to dispatcher to continue VM execution. So this shows us to how single opcode is processed and executed inside the PayIP. And there's a small but important note here. These opcodes are not static values is here because we have dynamic opcode table in the PayIP protection. They change at the runtime, so the values shown on the slide won't match what you see your own binary because as you can see, the PayIP has dynamic opcode table is here. Now that we know how the opcodes are built, maybe we can automate the process using the R2Pipe API. Since the opcode is created using the move and moveK pattern and then jumps to a handler function, we can write the simple Python script to detect the pattern and list the potential opcodes automatically. We are using some radar2 calls is here. We have analyzed this and we have seek function and we need to PDF JSON call is here. So it's a basic opcode pattern analyze script with the using R2Pipe. Let's run the example script and see what we get. Now we are switching to terminal screen and we can execute the Python script with the, we have the dump binaries, execute that. As you can see, we have the potential opcodes is here to the result. But one important thing is here, it prints out possible opcodes value that match this pattern. They may not all be real opcodes, but they give you a usable starting point for the analyze and save a lot of time to doing reverse engineering. So there has some potential opcodes. It's not definitely opcodes. Come back to the slide. As you can see, we have the same result in the terminal screen on the slide. And we have the opcode table finally. Here we can see the opcode table that we got a result of this analysis, but you never forgot this a little note. Okay, the final part is string encryption. The PayIP uses the same magic key across all of its bytecode files. It can be found to heuristic scan technique. So this key starts with this pattern and same across the all PayIP protected apps. This formula is XOR based formula, this simple formula based working. The easiest way to find this is by comparing your bytecode files. If they share a similar pattern, they probably the same key use it in all of them. But the one important things, if you have the new PayIP version this year or updated PayIP versions this year, maybe this key is not work for you because this key is constantly updated. So if you try to decrypt the new PayIP version, maybe you will fail with this key. So that is an important thing. So you can even verify it with simple tools like XXD and DD. As you can see, they have same pattern like AB16 and same pattern like this. This means we have the common key in the all of these binaries. If we apply the same formula with the recovered key, the formula is this. We can successfully extract the original strings from the binary. I wrote a small Python script to do this, and when we run it, we get the readable strings back, which is exactly what you want for the analysis. So we have to readable strings is here, like because action down, looks like it's is a logcat strings, and other library names is here. So we can successfully extract the two strings is here. And it's the final. Thank you so much for the listening. I really hope I didn't bore you too much with all technical topics. I am a bit of sick today, and I hope it didn't affect the presentation too much. Big thanks to Radara team for letting me share this talk with you. See you next time. Bye bye.